what about the standard error of ax plus b? This is equal to the absolute value of a times the standard error of x, right? B doesn't change the standard error, and what matters about a is its magnitude, not its sign. Okay? So what's the standard error of this random variable in standard units? The standard error of 1 over SE of x times x minus e of x over standard error of x is equal to the absolute value of 1 over the standard error of x times the standard error of x. Okay? Yes? Why are we doing this? Well, we're looking at what the mean and the expected value and standard error are of a variable after you convert the variable to standard units. And the reason we're doing that is we want to get things on the same scale so that we can apply the normal approximation, because the first step in using the normal approximation is to put things on the same scale. So the scale is standard units, so that when you transform to standard units, the new random variable has expected value 0 and has standard error 1. Okay? The normal curve, the standard normal curve, if you thought of it as a probability histogram for a random variable, so if you imagined carving it up into tiny little bins and letting those bins get infinitesimally narrow, right? So that probability of an outcome is going to be the area, an outcome in the little range is the area of the little bin. If you think of this as a probability histogram, divide it smaller and smaller and smaller and smaller, what would the expected value of the corresponding random variable be? Well, this thing is symmetric around x equals 0. The balance point is going to be 0. The mean of the corresponding distribution is 0. And it turns out that the standard error, the measure of sort of width of this thing, is 1. So if a random variable had a probability histogram that was approximated perfectly by the normal curve, that random variable would have expected value 0 and standard error 1. So if we want the normal curve to be a good approximation to something, we're going to start by transforming the units so that that something has expected value 0 and standard error 1. Right. So this is sort of going in the other direction. In this case, the normal curve has been shifted and stretched so that the balance point is the expected value of this random variable. We're looking at we're drawing 3 times from this box of numbered tickets. So what's the expected value of the sum of 3 draws from that box of tickets? Okay, it should be 3 times the average of the numbers on the tickets, right? If you look at those, they balance at 2. 3 times 2 is 6. The expected value should be 6. Expected value is 6. Okay? And then what's the standard error of the sum of 3 draws going to be? It's going to be the square root of 3 times the standard deviation of the numbers on the tickets in the box. So that turns out to be 2.44. So sort of the typical width of this is plus or minus 2.44 around 6. Okay, on average, things are 2.4. The square root of the expected value of the square of the difference between the random variable and its expected value. Yes, I think I actually even said that correctly. Is 2.44. All right, that's a measure of how spread out the probability histogram is. Okay, so here we have this theoretical curve. It's the normal curve that's been rescaled so that it balances at 6 instead of 0, and it's been stretched to have width 2.44 instead of width 1. Uh-oh. And the claim is going to be that this has something to do with the probability histogram of the sum of 3 draws from this box. So the question is, does it? Well, let's have a look. So we're now sampling from the box and getting the empirical distribution of of the sum of 3 draws. Let's do this a bunch of times so that we're not looking at sampling variability as an issue. All right. Now, here, in fact, you can only get integer values for the sum of 3 draws from that box. And the area under this corresponding curve has a lot of, it's non-zero area for values in between, not just values, little ranges of that box. But if we make this histogram a little bit cruder, then it starts to look like a better approximation. Yes? Okay. It's not going to be a great approximation because the sample size is small. If we increase the sample size, we're going to find that the curve does a better job of fitting the probability histogram. So let's go to sample size 30, and let's up the number of bins to 100, and let's take 1,000 samples. Okay, so here there are some values that are a little more common than the normal curve would predict, but we're getting a better fit overall.